Hello everyone, welcome back to your channel Physics Safari. I'm Abhishek and this is the fifth video lessons on the basic arithmetic. Today I'm going to discuss with you the second order derivative, maxima and minima, followed by the integration. And I'm going to keep this relevant to the physics because this is not the maths class. So I'm going to keep it as possible, relevant as possible to the physics. Now, so in the previous classes I have done the trigonometry, the binomial expansion, the quadratic, the parabolas, and the differentiations, derivatives. Today, let me help you to understand a second order derivative. So, for example, let's say if I have y equals maybe 2x cubed minus 2x squared plus 1, something like this. If I want to differentiate this with respect to x, well, already I've taught you these things. This is going to be 6x whole square, negative 4x, and this is a constant. This is going to be 0. Going further, if I want to differentiate it one more time, so I can write it as d square y upon dx square, which is nothing but differentiation of dy upon dx. All good? So this means I'm going to differentiate this with respect to x one more time. That is going to be how much? 12x and negative 4, and this being 0, so forget it. So that is the meaning of second order derivative, because I'm differentiating this y with respect to x for 2 times, so this is called second order derivative. Maybe we can have one more example. Let's say this time I choose y as maybe as a function of t, so I can have t square negative or maybe plus 2t plus 1. If I differentiate this with respect to t, for the first time it is going to be how much? 2 times of t plus 2, this is going to be 0. And in case of second order differentiation, this is going to be just 2. So this seems to be a very simple and the basic one. All good? Now, let's have one more function. Let's see one trigonometrical function, and we are going to differentiate that for the 2 times, that is the second order derivative. Let's say example 3. If I have y equals to x sine x, I have taught you the product rule. I've also taught you the quotient rule and the chain rule. If you have forgotten that, you can recheck the previous video. Now here we have 2 functions, x and sine x. Maybe I can keep it as u and this as v, and as we all can see, both are function of x, so we can use the product rule. So dy upon dx, if I look for the first order derivative, I'm going to keep x as it is. Sin x is going to be cos of x plus, I'm going to differentiate x, which is going to be 1. Sin x becomes, sin x would this time will remain as it is, so x becomes 1 times of sin x. So this is my first order derivative. And let me try and differentiate this for the second time. So d square y upon dx square. This again, we have 2 functions. I'm going to apply the product rule over here. Keep this u, v. So x, differentiation of cos x is minus of sin x plus, let's keep cos x as it is. Differentiate this. That is going to be how much? Just cos of x. And this alone is going to be differentiation of sin x is going to be cos x. So you can see that d square y upon dx square is going to be negative of x sine x plus 2 times of cos of x. If I look at this carefully, this is nothing but your function itself. So this could be written as what? D square y upon dx square negative of y plus 2 cos x. This looks like sort of d square y upon dx square plus y is equals to 2 cos of x. So yes, this is how you can do this. All good? Now, I would like to tell you a couple of things before I go further and drop you with some more example. If I have a function which is the displacement, if I have the suppose f of x is representing the displacement of an object. and it is varying with respect to time, it is changing with respect to time, then if I differentiate this, okay, maybe if I'm writing it or with respect to, let's suppose x as of now, I can do that. So it's displacement, which is a function of x over here. If I differentiate that with respect to x, normally we're going to follow this. Now, let us say that if I have a displacement as a function of time, that means if it is changing with respect to time, in that case, if I differentiate ds with respect to ds upon dt, that is displacement with respect to time, in that case, this could be written as d upon dt of ft, and my dear, rate of change of displacement is called as velocity. This is going to give you the instantaneous velocity. All good? Further, you also know that if I differentiate the velocity, that is rate of change of velocity with respect to time, is called as acceleration. So just for your info, anyways, I'm going to deal with these things in detail in the kinematics. So if I want to find the acceleration, you just have to differentiate v with respect to t. Just for your info, you might have studied this in class 10. A is equals to v minus u upon t. What is v? The final velocity. U is the initial velocity. So I can actually say that A is all about rate of change of velocity. Rate of change of velocity. In the terms of differentiation, this could be written as dv upon dt. Likewise, velocity could be written as rate of change of displacement. So, the velocity could be written as ds upon dt. So, these two fundamental things I want you guys to know. So, that is the reason why I have told you this. We'll be doing the detailed analysis of this later on. Let's say I probably put across a question for you. You can just note it down. I'll just drop down a question for you. Okay, you can just note it down. Meanwhile, I will write the question. So let us say I have example 4. Displacement, if I write as 5t cube minus 3t square plus 2. Now, I want you to find the velocity and the acceleration at time t is equals to maybe 2. The question could be like this. Find. So, they must define it like this is the displacement of a body with respect to time t. Find velocity and the acceleration probably at time t equals to 2 seconds. If this is the format of the question given to you, you need not worry. You need to understand one thing, that this is what you have already. So let me first find ds upon dt. Why am I doing it? Because this is going to give me the velocity. So the velocity, as we all know, it's ds upon dt. Now, let's say what? This is going to be how much? 15t square negative 6t and of course plus 0. So I have got the expression of velocity. At what time do we need to find? At time t is equals to 2 seconds. So the velocity at time t is equals to 2 seconds could be easily found out as replacing the t by 2. So we'll be having 6 times of 2. So that is 4 square. 2 square is 4 times 15 is 60. 60 minus 12. That's going to be how much? 8 and 4. So this is 48 meter per second. No big deal. Yep. Now I want to find the acceleration. So let's suppose I want to find the acceleration. That we need to differentiate the velocity for one more time, which eventually could be seen as double differentiation of s with respect to t, where s is the displacement. Well, if I do that, I'm going to differentiate this part. That should be how much? 30t negative 6. I would like to know its acceleration at any time t is equals to 2 seconds. So the acceleration at time t is equals to 2 seconds should be how much? 30 times 2, -6. That's too much, 60 minus 6 is going to be 54 meter per second square. Crazingly high. It's damn crazy, but it's okay. We just have taken a normal sort of example. So it could be anything over here. All good. So this is how, when we have the displacement and the velocity is is given as a function of time, and we are supposed to find the velocity or the acceleration. And this is how we can go ahead and approach the question. Now let me give you a question where I would help you to draw the graph of that, because I want all of you to be kind of very much good in drawing the graph. So let's say if I have example maybe 5. Okay, let me just clean that part also. Okay, anyways, let us see that. If I have S is equals to t square minus 2t plus 2. Well, that is the displacement as a function of time t. I just want you to plot the graph of the displacement versus time graph. So plot S t graph for this one. Now, why am I doing this? Because I've taught you lines, if you remember. I've also taught you the parabola. So I just want to see whether you guys can do it or not. Maybe you can pause the video and take 2 minutes and try this out. All good? Alright then, once you're done, let us see how to approach this question. Well, first of all, whenever we have to plot the graph of any two variables, let us draw them first. Maybe I'm going to use this part. So let us first draw the axes. So here we have, let's say this is your S axis and this is your T axis, S and T. Now the basic criteria is to find at time t is equals to 0, where is the body, and at what time the displacement is 0. But before we get into that, this looks like a parabola for sure. This looks like to be a parabola. Now, since the coefficient of this is positive 1, it means the parabola should be opening upward. All good? Now, there are two methods to find the point where the parabola is achieving its minima, because in this case, it is going to be upward. So, the point of change, the vertex, we have to find. So, one way is to go approach with the concept of parabola, and other is to approach with the concept of maxima and minima. All good? So, first of all, let me help you to understand with the concept of parabola. Now, you know that the vertex form of the parabola that I've taught you should be given as the vertex form of the parabola. Vertex form of parabola. So, if you guys remember my probably the second or third video, in that it is given as x minus h whole square is equals to 4 times of a y minus k. Then we have x and y axis. And this basically is going to represent the parabola with vertex h comma k. Somewhere like this. Let's say h comma k. Over here, in place of y, what we have? S. In place of x, what do we have? T. So this parabola graph would probably look like this. How much? T minus h whole square is equals to 4 times of a s minus k. Well, this should be the standard form that we must achieve. And if you look at this, this is a perfect square. This is a perfect square. So one more technique I'm going to help you to understand. Let's say how to make a perfect square. Now here we have s equals to this t square minus 2t plus 2. So maybe I can use this part. So let's say t square minus 2t plus 2 is equals to s. We know that a minus b whole square should be a square minus 2ab plus b square. Keep that in mind. Now having that over here, let's say this is going to be t square. This should be written as 2 times t and of course 1. This one synchronized. If it is 1, then it should be b, right? So I should have 1 square. So make sure that it is falling in this pattern. All good? Now if it is 1 square is there, which I'm adding from my side, let me subtract 1 square and this plus 2 already it was here. That should be equals to s. If you look at this entire thing, this is going to be how much? T minus 1 whole square. 2 minus 1 is plus 1 equals to s. So you're going to get what? T minus 1 whole square equals to s minus 1. That means the vertex of this parabola should be 1, 1. Look at this. All good? The vertex that we have got is 1, 1. It means the vertex of this graph, this parabola, has to be at point 1, 1. Definitely that is going to be somewhere here, maybe 1, 1, somewhere here. Now what next you need to find? You have to figure out at what point it is intersecting the s axis, and probably t axis it is not going to intersect because the parabola is going to go up. So to find s intercept, t has to be 0 because on this axis the t should be 0. If I look at this expression and t has to be 0, it means that would implies what? This implies s is going to be 2 for t equals to 0. It means somewhere here at 2 the parabola is intersecting that, and this is the point 1, 1, the vertex. So can you just say the parabola has to be like this? Okay, like this. So this is the graph of this function. This is the displacement time graph of this function. Now the point, my dear, is this is the displacement time graph. Not all the time I would be getting a quadratic equation like this. So we should know some other concept which can help us to sort of solve these kind of questions and draw the graph properly. The drawing the graph is very important. It's very essential. Okay, so first of all, you guys just process this one and sort of draw it out. Just process it carefully. Understand this part properly. Okay, so let us see. If you're done with this, let me help you to understand the concept of maxima and minima. And I'm going to show you how we can draw this graph with the help of maxima and minima quite easily. So let me have it here. Let me just have it here. Now, well, if I have a function, probably let me choose this function itself. Maybe y is equals to x square minus 2x plus 2. I want to see at what point this is attaining the maxima or this is attaining the minima. So before I get into that, let me help you what I actually understand by the minima and the maxima. Just for example, let's suppose if I have a graph like this. Check it out. At this point, it is attaining the maxima. This is the point of maxima. We can have local maxima, local minima. You're going to study that in terms of maths. And let's suppose this is a point where we have the minima. Because this is a minimum value, right? So this is the minimum. This is the minimum. One thing you can find common in both of these, that the tangent to these 2 points, is going to be parallel to x-axis. See this out. The tangent is parallel. Tangent is parallel. So one criteria that we have understood now for maxima or minima, the slope has to be 0. And what is slope? Slope has to be 0. That means dy upon dx should be 0 because slope is what? Dy upon dx. Already we have discussed about this in the previous video lessons. So dy upon dx has to be 0. Now this is going to help us to find the points where the slope is 0. Right? Because line which is tangent, if it is parallel to x-axis, parallel lines will have 0 slope, perpendicular line will have the infinite slope. Now once I'm done with this, we now need to decide whether it is a maxima or the minima, whether the point that we have got is giving you the maxima or the minima. Now let us understand one thing. If I look at this portion separately, so let me draw that portion over here. Maybe I can just, let's say if I look at this portion. At the top point over here, the slope is 0. If I choose a point towards its left and I tend to draw a tangent, see this out. Its slope, it's going to make some acute angle. It is going to have positive slope. So towards left of this maxima point, this top point, we have a positive slope. And let's say I choose a point towards right, and I try to draw a tangent. Well, this is going to make an obtuse angle. This theta is going to be obtuse. It means the slope is going to be negative. If you remember our thought, if the angle is obtuse, which is in second quadrant, the tan is going to be negative, and if the angle is acute, it's going to fall in the first quadrant, and tan is going to be positive. And we know that slope is all about tan of the angle, which the tangent makes with the exact sorry about that, with the x-axis, right? So from negative it became 0. From the positive it became 0, and then it became negative. It was actually a positive quantity earlier. I'm talking about a slope. It became 0, and then it became negative. If I want to find the change in the slope, let's suppose delta m, change in slope. So delta m final minus m initial is going to be how much? Is going to be how much? A negative quantity minus a positive quantity. So negative minus positive and negative, that's going to be overall, this is going to be a negative quantity. It means change in the slope is negative. Now let me write this in terms of maths. Change of slope with respect to time, or maybe I can say with respect to x, if I choose this as x and y axis, let's say, with respect to x is negative, isn't it? Positive, 0, negative. If I move from left to right, make sure you move from left to right. What is slope? Slope is all about dy by dx. So can I say d upon dx of slope, which is again dy by dx, is a negative, that means lesser than 0. That means d square y upon dx square is less than 0. For what? For maxima, for the point of maxima. Isn't this guy clear? Now let me tell you something. If I talk about this expression in particular, this is nothing but rate of change of slope, rate of change of slope. So double differentiation of y with respect to x tells you the rate of change of slope. So one thing is quite clear now. At the point of maxima, the d square y upon dx square has to be lesser than 0, which means it's a negative quantity. So that is the second criteria. First was here that dy upon dx has to be 0. Now the second criteria, that if d square y upon dx square is lesser than 0, then that point is going to be the maxima. Likewise, if I choose, probably, okay, let me write here. Let's say if I look at this point of minima, let's suppose at this point, check it out. If I choose another, if I move from left to right, let us take one point over here. And at this point, if I tends to draw a tangent, that should be having a negative slope, right? Because this theta is going to be obtuse angle, so the slope has to be negative. It means at this point, slope is negative. At this particular bottom point, slope is going to be 0. And if I choose a point over here, the tangent, if I draw, that's going to make an acute angle, let's suppose alpha, which means the slope is going to be positive. It means the nature of change of slope from negative to positive, that clearly indicates that the rate of change of slope at the minimum point is going to be a positive value. So d square y upon dx square is going to be a positive value. So I have actually derived or obtained all the possible requirement that for a maxima minima, slope has to be 0, which means dy upon dx has to be 0. And if I differentiate it for the second time and I get some negative value, it means I have reached, that's a point of maxima. And if I get a positive value, means that is the point of minima. All good? So you can summarize this quite easily. For the maxima minima, slope has to be 0. So you're going to do step number 1. Differentiate the function with respect to the variable. Equate that with 0. Get the point where the change takes place. Now, in order to decide whether the point is maxima or minima, you must differentiate that function for one more time and check if it is a positive or negative. And accordingly, you can decide if it is positive, that point is a minima, and if it is negative, that point is maxima. Well, this is what we need for the physics. There are a lot of applications of maxima and minima we have. For example, a very simple example that you come across in class 12 in the calculus in application of derivative in maths. That if the rate of change of radius is this much, what's going to be the rate of change of the volume of a sphere? Probably, if the body is moving, away from the torch, or maybe the, what do we call that? The lamp house or the lighthouse. The shadow is going to be sort of, increasing. So what's going to be the rate of change of shadow and stuff like that, But I'm going to keep it as relevant to physics, okay? Now, let us use the same concept to help us to draw the graph of this line. I'm like this equation. Of course, that's not the line, okay? So, you guys, if you have not noted it down, you can pause and you can just note it down. Now, let me just quickly erase it up. Okay. Almost done. Great. So now, if I say, let's say, okay, let me just erase this part also. So let's say if I have the displacement versus time graph given as t square minus 2t plus 2. So that was the question. I wanted to plot the graph. So first of all, I want to check with the first order derivative, and I'm going to equate that with 0. So first of all, let me do this. Now for the maxima or minima, what do we know? For maxima or minima, ds upon dt has to be 0. That implies 2t minus 2 should be 0. That means t minus 1 should be 0. That implies t is going to be 1. See, we have got it. Right? Now, if t is equals to 1, I can easily find the value of s. So, that implies s is going to be how much? 1 minus 2 plus 2. These two will get cancelled. We'll be having s also equals to 1. So, I've got a point where the graph is achieving its maxima or the minima. Now, the second thing that we need to understand whether it is a maxima or the minima. Okay. So, the point that I've got is, if I write s comma t, probably t comma s, that should be how much? 1 comma 1. Let us figure out whether the point is maxima or minima. So, for that, we have to differentiate this for one more time. So, let us find d square s upon dt square. Well, that is going to give you how much? If you look at this part, okay, d square dt is going to be 2. I think that got erased up. So, this is going to be how much? Just 2, which is a more than 0. It means this point is the point of minima. So, first of all, let's have it. The point of minima is achieved at the point of what? 1 comma 1, right? Isn't it? And that's the only point. Because we do not have dependency on t over here. So that I could have just substituted the value and checked out. Just like it's going to be more than 0, so it's going to be a negative. It's going to be having a minima itself. Of course, at which point? At this point. I have that point where I'm going to get the minima in. Now again, I want to find where it is intersecting the s-axis. And let's suppose this is t. For that, I'm going to put t is equals to 0 over here. If I put t is equals to 0 in this equation, at t is equals to 0, s has to be how much too? Somewhere here. It's a minima, so the graph is going to be like this. As simple as that. So this we can do easily with the help of concept of maxima and minima, which we have done with the help of parabola in the previous case. All good? Now, let us move on to the next part, and we shall discuss something on the integration. I'm sure it's okay to you. If you want, we can do some more practice question up here, and probably I'll be doing more of it when I'm going to teach you the kinematics. So in this class, I just tried to give you a basic understanding of the maxima minima and how it can be helpful to us in sort of plotting the graphs and all. Okay, now the next is the integration. Integration. Again, the basics for this is required, and of course, whenever it is required in while doing the classes, we can do it. Okay, so let us, before I get into this integration and give you the direct formulae, let me just tell you something. Let's say I have a square of side A, and I want you to find the area. You probably will do what? A square. All good. If I have a triangle, maybe this it's equilateral triangle. I'm gonna ask you to find area. Will be do okay. So root 3 upon 4 times of A square and stuff like that. Even if it is a circle, you can find by pi r square if it is r. So when we have a well-known quantity, well-known shapes, figures, we can easily find the area. Okay. Now, let's say if I give you a certain sort of, let's say here we have some graph like this, maybe like this, and I ask you to find the area. Maybe in this region, let's say this is upon x initial, and this is your x final, and this is your y-axis. Let's suppose this is your x-axis. I want you to find the area that this curve and this x-axis encloses in this region of xi and xf. Basically, I'm asking to find this area, area of this region. Now, you do not have any particular idea about this thing, right? So this is, let's suppose I have given you, this is a function y is equals to f of x, some function of x. This graph is a function of x. Apart from that, nothing else is known to you. So maybe if I ask you to do that, you probably would try to do what? You will try to probably make some rectangular boxes over here, and maybe you can just add them up, and that's how you can achieve the area, because we have no idea about this shape, but certainly you know something about the rectangle. But this area is not going to be that close, that precise. This is going to give you some approximate area, right? This is not going to be that accurate. So what are you going to do? Probably, you might try and make smaller strips. You might try and make some more strips. You're going to increase the value of the number of strips, and that will make it more accurate. It's going to be more closer to the accuracy. So probably, some other guys, let's say he wanted to become more precise. He made some more strips and all stuff like that. And of course, his answer is going to be better, closer to the actual answer. So what is happening over here? Let's say if I just remove it. So exactly if I choose this length as dx for these two strips, and this length, let's suppose I choose as y, height. And we have, let's suppose, n such strips. So the total area should be what? Area of one strip plus, and so the area of all the n strips. So that would be how much? Y, it's a rectangle, so y times of delta x, plus maybe y2 or something like it, that y2 delta x, and so on. Now, so I can say that area could be given as area 1 plus area 2 plus area 3, and so on. So in terms of mathematics, if I want to add them, I can do what? I can apply the sigma of all the areas. So that could be, let's suppose, y delta x, and the limits of x should be how much? To x initial to x final. So that is going to be the area. To get more precise area, if I shrink it almost close to 0, so that would give you what? Infinite number of such strips, as in, let's suppose the number of rectangular strips. Understand this carefully. Rectangular strips is n. If I have less number of n, it means the accuracy of the area would be less. If I increase the value of n, the accuracy will also increase. It's going to be more precise. And in that case, delta x would decrease. The thickness of each strip is going to decrease if I increase the number of n for this given set of range. Of course, the number of sides of the strips would decrease. So gradually, if n tends to infinity, it means we can have infinite number of such strips. In that case, delta x would tends to what? 0. delta x would tends to 0. So we are arriving somewhere in the zone of limits. So to get the approximately the best possible area, if a tends to infinity, delta x will tends to 0, and that's going to give you the more accurate, or you can say the entire accurate area. So can you just say that area, if I put limit delta x tending to 0, sigma of maybe xi to x final, y times of delta x. And we have seen before that when delta x tends to 0, this could be written as what? Dx. And this sigma, which is used for the discrete particles, these are the discrete individual areas, right? They were the discrete particles. The sigma is a mathematical tool that is used to add up the discrete particles. Now, since this becomes almost zero, it means this is not going to be discrete any further, but that's going to be a continuous path. So, my dear everyone, can I say that this could be written as, area could be written as y dx, and this sign would change to the sign of integration, where initial, the lower limit should be xi and the upper limit is going to be xf. And my dear everyone, this is called integration. This is called integration. So integration is a way to find the area for a continuous path, a continuous function. When I integrate the function with respect to the variable for a certain limit, it could be for the infinite limit also. But for a certain limit, I'm going to get the area for the certain region between the curve and the x-axis over here in this particular question. And this is the way to write the integration. In class 12, in calculus, you will be having entire studies about the integrations. But since we're going to need this for the physics in class 11th itself, we must know this. So what does integration help you to do? It actually gives you area under curve. Area under curve is all about, if I talk about the curve with y and x, is given as y times of dx. If you want to make it a finite value for a certain region of x, you must put the limits. Well, this is called the limits, the lower limit and the upper limit. This is called a variable. All good? Now, so having done this, we must know certain basic fundamental rules which we can use to do the integration. So let me quickly help you with that. Some fundamental rules of the integrations. Well, integration is also called as antiderivative. It's just like opposite of derivative. So I'm going to show you a couple of examples, couple of rules for the integrations, and maybe we can do some questions. Okay, the first fundamental rule, my dear everyone, is going to be like this: x to the power of n, integration of x, and this is going to be x to the power of, the power would be added over here, and we are also going to divide plus a constant of integration. Now, rule number 2. But before that, let's have an example based on this rule. Maybe I can say x to the power of cube, and the variable is dx. It is changing with respect to dx. In that case, we'll be having what? X to the power of 4 upon 4 plus c. All good? You can ignore this c for now. Let's say if I probably take a limit integration when we have x square dx, and I put a limit at 2 to 4, maybe 2 to 4. So that would be what? X to the power of 3 upon 3, and let's see how to evaluate the limits to 4. So I'm going to put the upper limit first, and then we're going to subtract, and then we're going to put the lower limit. That's how the integration is supposed to be done. We have 4 to the power of 3, and this 3 would remain as it is. Put a minus sign. Put this lower limit. Replace this x by the lower limit. That's going to be 2 to the power of 3 upon 3 as it is. So this is going to be how much? 64 upon 3, and this should be 8 upon 3, isn't it, my dear? That's how we're going to do it. So yes, you can take the LCM, 3. It should be how much? 56. So 56 upon 3 is the integration of this. So this is basically all about The area between x square and the x-axis where the x changes from 2 to 4. It's a parabola. It's a quadratic parabola going up. That's how we're going to get it. Okay, all good. Now, the second and few more rules of integration. Let's suppose number 2, integration of a to the power of x would remain same. That is going to be e to the power of x itself, and maybe we can have e to the power of minus of x. In that case, this is going to be e to the power of minus of x, and of course minus 1. Maybe if you look at the sign, x integration dx, that is going to be minus of cos x. So the differentiation of sine was cos and the differentiation of cos was minus sine x. So the sine took the revenge over here. And that's how I do remember, I always think the cos is probably not that good guy, and the sine is a good guy. Now, let's say 5. Maybe if I talk about the cos of x dx, its integration is going to be just sine of x. Maybe secant square x, integration is going to be tan of x. You can actually get all these rules over here in the books written. Maybe I'm more interested to teach you the concept, or rather just telling you these formulae, which probably you can get quite easily. Okay, one more I would just like to help you with. 1 upon x dx is going to be log of x. So yeah, I think that should be okay. That should be okay. And maybe we can just try one more with maybe like if I say cos square x, maybe cos square x. Yeah, let's keep it x. If I ask you to integrate this, please do not do this cos 3x upon 3 plus c. No, this is wrong. This is not the right way of approaching this kind of integration. So what you must do over here is, if you remember, I have given you a formula, right? And that 1 plus cos of 2x is 2 cos square of x. This 2, and I've also given you 1 minus cos 2x is equals to 2 sin square x. These are the two of my favorite formulae when it comes to trigonometry, because they are really helpful. They helps you a lot, like the way it's going to help you now. Could you just write this cos square x as what? 1 plus cos of 2x upon 2 integration. Now it could be done. I'm going to split this. It should be 1 upon 2. You just separate this. You can also do that in case of integration. Cos 2x upon 2 times of dx. You can actually separate the integration if it is with the plus or minus. 1 upon 2. Okay, integration of any constant, my dear. Maybe rule number 7 was there, so rule number 8 I can put it here. Integration of any constant, a dx. Well, a could be taken out and we'll have dx, and the integration of dx is going to be just x. So this is going to be ax. Keep that in mind. Quite a time you're going to have this in physics. Okay, coming back to this one, 1 by 2, if you take it out. So 1 by 2 is out. Integration of x is just dx is x. Or I can take this 1 upon 2 common. Cos 2x. Now remember, sin x. So here we have sin 2x, coefficient of x. You must divide by 2, the coefficient of x. So yeah, that is it. So your answer has to be x upon 2 plus sin of 2x upon 4. That is all. Okay. So we will stop here only. So that brings us to the end of this basic mathematics. Next is going to be the vector or the kinematics. So vectors is very essential to understand before we jump into the kinematics. So the next is going to be the vector. So I believe you guys have understood all these basic fundamental maths required for the physics. I would suggest you to practice some more on the concept that we have given you. All good? So yeah, keep learning and keep studying. And thank you for watching. Probably I'm going to see you guys very soon in the next video. Till then, take care. Bye everyone.